I wanted to continue our discussion about the Gibbs free energy by talking a little bit about standard conditions. This is something you should have discussed in Chemistry 1A. However, it didn't actually matter all that much. It turns out it matters quite a bit when we talk about the Gibbs free energy. So we're going to go ahead and go through some of these details in the recorded session, and then when we have the live session, we will go through why it matters. So there are a set of conditions that we use to define the standard state. For a gas, we would have a pure gas at exactly 1 atmosphere. So if it's a mixture, we would not have standard state. If we have a liquid or solid, it is a pure substance in its most stable form, again at 1 atmosphere. And the temperature is usually 25, but we might be given additional information about the temperature as well. If it is a solution, the substance has a concentration of 1 molar. So these are the standard state conditions, and when we look up information on a table, we're typically going to be looking up standard state information. So here we're showing that, so similar to enthalpy and entropy, we can look up the free energy of formation for any substance at standard state. So again, the degrees symbol, we call this naught, so delta G of formation naught is the standards at standard state. And so when we look these up in the tables, that's what we're looking up. We're looking up the standard state values. Similar to enthalpy for the Gibbs free energy, the elements in their pure forms have standard states of 0. And we can see some other values for some of these other things here. So we want to know how to calculate the delta G of formation at standard state at 25 degrees Celsius, at other temperatures, and then stepwise from other reactions. So these are the things we'll be looking at. And basically, this is how we do these. For reactions at 25 degrees Celsius, we basically just do the same thing we've done for enthalpy and entropy. We look up the values in the appropriate table, we add up the products, and then we subtract the summation of the reactants. So again, basically using Hess's law. So we've gone through some examples of that already with both enthalpy and entropy. So it's the same thing here. The main thing is that you know which table to look that value up on. You might be looking up tabulated values. So again, similar to either enthalpy or entropy. And then if you're finding the Gibbs free energy of formation for pure elements and their standard state, it will always be 0. Okay, so this is how we would do this for a reaction at 25 degrees. If it is at some other temperature other than 25 degrees, we can't just look up delta G, because then there's an entropy effect as well. So instead of this, we would look up the enthalpy of formation and the entropy of formation. We assume that the changes to these values based on temperature are fairly small. You'll learn to make adjustments to that later if you need to. And then we use this equation. So it's basically the equation for Gibbs free energy. So the delta G of standard state at standard state of the reaction is equal to the delta H at standard state of the reaction minus whatever that new temperature is times the delta S at standard state of the reaction. So this is how we account for changes in delta G at different temperatures. In this case, we would look up both delta H and delta S instead of looking up delta G. We might also have a case where we are expressing things as a series of reactions, and we could use the more general definition of Hess's law in that case. So again, we can add up the individual reactions to get the delta G of the overall reaction. If we reverse the reaction, we reverse the sign of delta G, and if we multiply it by a factor, we multiply delta G by that same factor. Again, same idea as we had for delta H. Okay, so there's basically three possibilities here, and which one you use depends on what you're given in the question. So the first possibility is using this idea of looking up the free energies of formation for the parts of the reaction. So if you're given enough data to do that, you would do products minus reactants, again, similar to things we've done before. If you're given something at a different temperature than what is listed on those tables, you have to account for that temperature difference by performing this reaction. So you would calculate delta H of the reaction, calculate delta S of the reaction, and then you would do this whole equation. So this part might look like doing the summation of products minus reactants as well as this part. So this second one could be a more involved problem than it looks like right now, because you might have to put together those other pieces to get to the full thing. And then the last one, if you're given not maybe tables, but some reactions, you can add those together the way we did with delta H in the past. So the first and last one here are pretty similar to things we've seen before. The complexity comes with the second one, where you might have to do a series of things together to get to your final amount. There are some examples here. I think what I will do is, because we don't in the asynchronous format have the ability to stop and ask questions, I think what I will do is let you go through these on your own. And if there's one of these examples we would like to go over together where you do have the option of asking me questions, then we can do that when we come back together. So you'll have to watch these and decide which ones you need additional help on in order to do that. So this first one is using that second possibility. So it's actually giving you that that's what you want to do, and it's giving you the delta H and S values. So that's a good one. Definitely I'd recommend practicing that one. So let's skip ahead to the next one. So here you're given, again, a value other than 25, and you want to do an estimate at a different temperature. And this is also referring back to the previous one. So you'd want to do 17.5 example before doing the 17.6 example. And then the next one, here you're doing this from the delta G of formation. So this will be more similar to that. I guess that would be the first one of the possibilities. So you can try that one out as well. And then here, this will be similar to that last one where you're given several reactions you have to combine together. So you might want to practice that as well. Okay. So again, we can go through any of those in detail in class if people would like to do so. Just a brief spoiler about what's coming up next. So everything we just talked about was at standard state conditions. The reality is almost nothing is at standard state conditions. So there's an additional thing we have to do to account for that. And that's where we're going next. But in order to get there, you have to really understand how delta G works, because we'll end up combining and combining and combining different equations. And you want to understand each one in order to know what the final combination looks like. So that is it. Please watch this before class, and we can talk about it more then if we need to.